Oh, this is on? Yeah, it's on already. Sorry? It's on already, yeah.
All right, welcome everyone to this week's CFA Colloquium. I'm very pleased to introduce Karin Sandstrom, as a close collaborator of mine. She's a faculty member at UC San Diego and actually started here at the CFA as an undergrad, and so that is maybe bringing back some memories. Karin has done a number of work on the dust and gas in nearby galaxies, a lot of the important work about a decade ago using Spitzer, and now she's going to tell us all about what we can now do with JWST. So Karin's been involved with a number of the nearby galaxy legacy programs that have been taken in the first few cycles of JWST, and today she's going to tell us all about those and specifically the polycyclic aromatic hydrocarbons. Please take it away.
Thanks. Well, thanks everybody. It's really exciting to be back. I have a lot of memories of being in this room. I used to sit up in the corner because I was intimidated. So it's very nice to be here. And it's also amazing to be back because of so many formative experiences here. 23 years ago is when I graduated. 4 years before that, as an undergrad, I took Science A17 with Owen Gingrich and Dave Latham. And that was the class that convinced me to go into astronomy. So very glad to be back to share this with you all. So today what I'm going to talk about is my favorite topic, polycyclic aromatic hydrocarbons. And this beautiful image you see here is a JWST image in the mid-infrared taken with the MIRI instrument of the galaxy NGC 628. And one of the very cool things about this is that nearly every photon that was collected to make this image came from the vibrational de-excitation of a polycyclic aromatic hydrocarbon. So even if you don't yet care about PAHs, I hope to convince you to by the end of this talk. So for some context, we'll start off with some history. So in the 1970s, some of the early mid-infrared observations of the ISM and the Milky Way and nearby galaxies started showing these features that popped up at very specific wavelengths. This is 11.3. These were initially called unidentified infrared emission features or bands, and there was a series of them that were evident in the spectra of galaxies, Milky Way nebulae, planetary nebulae, H2 regions, and they have these predictable wavelengths. The strongest are at 3.3, 6.2, 7.7, 8.6, and 11.3 microns. So shortly after that, in the 80s, lab work started to compare the wavelengths of these unidentified features to the spectra of polycyclic aromatic hydrocarbons. And you can see one of the key papers on this, Leger and Puget, in 1984, comparing this to coronine, and you see many of the same features. So this led to an attribution of these to polycyclic aromatic hydrocarbons. In general, this is expected to be some kind of hydrocarbon small grain, and I'm not super particular about the exact designation. Some people are, but I'm going to refer to these as polycyclic aromatic hydrocarbons, and happy to argue after the talk if you'd like, if you have a different favorite thing you would like to call them. This also led in the 80s to one of my favorite paper titles, so polycyclic aromatic hydrocarbons and the unidentified infrared emission bands auto-exhaust along the Milky Way. And this came about because of the comparison of the lab spectrum of auto-exhaust to the spectrum of the Orion bar, showing the same features. So on Earth, of course, PAHs are very toxic and you don't really want to breathe them in. But in space, they are wonderful. So PAHs, if we just did the basics, they are aromatic carbon rings with attached hydrogen. They make up around 5% of the total dust mass of the Milky Way, and they range in size from everything down to what you would consider a molecule. So the minimum sort of size of a PAH we expect in the ISM is around 20 carbon atoms in the diffuse ISM, all the way up to 1,000 carbon atoms or more. So 1,000 is just the bound on what you consider a PAH. Carbonaceous dust grain continue on from 1,000 to many thousands of carbon atoms. So the exciting thing about these is that when they absorb a UV or optical photon, they de-excite by vibrations. And there are many different vibrational modes. As the molecules get more complex, there are changes in the exact frequencies of these modes. And so they produce these broad vibration features that are associated with different kinds of vibration. So you can see here at 3.3 microns, there is the CH stretching. There's various CC stretching, CH in-plane bending. So there's all these different types of modes that produce these features. And what's cool about this, right, is that for other dust grains, for things that are bigger, we only get boring continuous emission. PAHs tell us about their conditions via these infrared emission bands. So by observing the different features, we can understand the state that the molecules are in. So just as a demonstration of this, one of the key ways that the spectrum of PAHs vary is if they are neutral versus ionized. So you can see here the spectrum of neutral PAHs are very bright at 3.3 microns and 11 microns. But then in ionized PAHs, those bands are faint. And the 6 to 7 micron range is much brighter. So with that information, we have the ability to go out and learn something about the ionization state of these grains. In addition, and this is a much more complicated figure, but we'll just talk about it briefly for a second, each of these different size grains is more or less efficient in emitting in the different features. So here you can see the efficiency of emitting in a given band as a function of size for both ionized and neutral PAHs. And I want to point out one of these in particular, the 3.3 feature. The rest of them all have sensitivity at some level to different sizes. The 3.3 pretty uniquely picks out small neutral PAHs. So this is a helpful handle on these grains. So at this point in the talk, you might be sitting here thinking, oh wow, I just signed up for a whole colloquium about a very specific kind of dust that maybe you're not totally sure you're interested in. So I'd like to give you a few reasons why you might want to care. And all of these fundamentally relate to the fact that PAHs are actually central to the way the ISM works. The first thing they do is they produce photoelectric heating. So some fraction of the time when a PAH absorbs a UV photon, it ejects an electron that goes on to heat up the gas. And in fact, for the neutral gas in the galaxy, PAHs are the dominant heat source. So the photoelectric effect from PAHs are the dominant heat source. In this situation, the actual dominant coolant of this phase is the 158 micron carbon plus emission line. So between PAHs and carbon, we have the whole heating and cooling cycle, essentially, of neutral gas, which is kind of exciting. PAHs, though, because they can become charged and have these different sizes, have a variable efficiency at producing photoelectrons. So the smallest PAHs are the best at producing photoelectric heating, and that comes along with their surface area and how often they recombine with electrons. And then they also become worse at photoelectric heating if they're charged. So the heating efficiency drops if the PAHs are charged. And so from this, the balance between heating and cooling is what sets the conditions for cold neutral medium and the formation of molecular hydrogen, which is where stars are going to form. So you should care about PAHs from the physics of the ISM perspective and care especially about their charge and size distributions. So in addition to setting up the conditions for H2 formation, PAHs actually may dominate H2 formation itself. So there are about 50% of the grain's surface area is in PAHs, and the formation of molecular hydrogen occurs on grain surfaces. There may in fact be very efficient routes through this H addition and H2 abstraction reactions that form molecular hydrogen on PAHs. So they are also very important from that perspective, forming the actual molecular gas themselves. In addition, and this may be something that people care about from a trying to observe other objects perspective or high redshift galaxies, PAHs are likely the carrier of the 2175 extinction feature. So this can be reproduced in the lab with combinations of PAHs of different sizes. And it's a very observable signature of the existence of carbonaceous dust. And in fact, now that this has been observed out to something like redshift of 8 with JWST observations, there are some uncomfortable questions presented about how you actually make carbonaceous dust at a time 600 million years after the Big Bang. So this is generally too quick for what people have often argued is the AGB route for forming carbonaceous dust. So this is an interesting puzzle that is starting to be addressed in high redshift galaxies. In addition to the extinction, the inverse of that, when they absorb all these photons, PAHs re-radiate a large portion of the infrared emission from galaxies. So around 10% of the total infrared comes out in the PAH vibrational bands. You can see these beautiful features in the spectra from the SING sample here. And because they are so bright and actually quite narrow, this makes some of them distinguishable, even out to high redshift as a tracer of the ISM. And this is a recent observation of a lensed redshift 4.2 galaxy where the 3.3 micron feature has been detected in this very distant galaxy. And 3.3 is quite a faint one, so this is impressive. It's just the last thing to kind of redshift out of the JWST spectroscopic filters, so something that's detectable here. Okay, so those are all exciting reasons. There's also a more kind of self-centered one, which is that PAHs are a building block of carbonaceous material in planetary systems. So we'd like to understand them from a perspective of life origins of solar systems and life and all of that as well. So this is a really cool recent observation from the Ryugu sample return mission that detected PAHs up to 61 carbon atoms in size by analysis of the return samples. So this is actually the first direct-ish measurement of PAHs that were at least once in the interstellar medium. Okay, so those are my reasons for you to care about what I'm going to try to tell you next. The interesting thing, though, once we get through what PAHs do, is that we don't technically really understand how they got there or where they go. So the PAHs are very important, but their life cycle is still really mysterious. So there's some evidence that they can form in the atmospheres of AGB stars. There may be routes for formation in the ISM. They're definitely destroyed and altered throughout the ISM. And they may be destroyed, especially in H2 regions or in supernova shocks. But almost all of these aspects of their life cycle are still relatively unknown. So for the carbon-rich AGB star winds, there's a well-known path to forming things through combustion-like reactions that also occur on Earth, like the auto-exhaust sort of route. So the problem, though, is that when you count up the number of AGB stars in galaxies and their dust production rate, it doesn't seem to match the amount that is needed to explain how much dust is there. So this is an interesting problem. It may be that there's enough time variability and big spikes in dust production that this can be reconciled. But it also doesn't quite gel with the fact that now you see it at redshift of 8. So how do you form these? Another route may be something like shattering of larger carbonaceous grains. And then when you have these fragments, if you expose them to UV radiation, you can break off all the parts that are not strong aromatic bonds. And this is called aromatization. So the PAHs that have non-aromatic carbon attached are called aliphatic components. And you can basically rid the PAHs of these aliphatic components by irradiating them with UV photons, potentially. So that is one route. Another that's really exciting, and this is more recent, and your friends down the road at MIT, Brett McGuire and his team have done a lot of work on this, is showing that there are possibly gas phase pathways for forming PAHs in molecular clouds, and they have gone on to detect many PAH-like precursor molecules at very high abundance in cold clouds, at an abundance that can't be explained by typical routes and may suggest much more efficient ways to form PAHs in the ISM. So basically the picture is that we don't have a clear path. It's probably some combination of all of these things at some level, but it would be great to understand more about where these dust grains that control so much of ISM physics come from, and then how they are destroyed. So what we are attempting to do with nearby galaxies is map the abundance and properties of these grains across the ISM of nearby galaxies and help us understand where they are forming and where they are destroyed. So that is what I will be telling you about today. And we also get to use these beautiful JWST images to do this. So this is one of the galaxies from the FANG sample, which I'll tell you about in just a moment. So we are in luck. With the launch of JWST, we now have one of the best possible things we could want to observe PAHs. So JWST has both imaging and spectroscopic capabilities that cover the wavelength range from 3 to around 17 microns, where these features are very bright and detectable. They have a number of photometric filters in particular that are specifically sitting on top of bright PAH features. So for NIRCam, this combination of 3 medium bands around 3.3 microns sits right on top of the 3.3 PAH feature and gives you these kind of flanking filters that let you subtract starlight and other things from your map. So this is very handy, extremely useful for mapping the 3.3 feature. And then MIRI, helpfully, has filters that sit specifically on top of the bright PAH features. So this includes 770 wide, which is sampling the 7.7 feature, and 1130 wide, the 11.3 feature. And thankfully, these are specifically designed actually to bracket these different PAH features. So we have amazing imaging capabilities to map these. And the spectroscopy from NIRSpec and MIRI covers the full spectrum of PAH features, showing in great detail. This is a beautiful spectrum from the PDRs for All program. And you can see actually features that we never would have known about, including one right here, which I'm going to tell you about at the end of the talk, giving a whole new window into all of these interesting vibrational bands that these PAHs emit. So let me start by telling you about how we map the abundance of PAHs across nearby galaxies. So to do that, we make use of the way that dust behaves when it's illuminated by a given UV radiation field. So here you see the emission from a population of dust grains illuminated by a radiation field that's scaled up and down the solar neighborhood by a factor of U. And you see 2 distinct things in this plot. So in the short wavelength part, where the PAHs live, all of these collapse onto one line. And that's because this is stochastic heating. So the grains, the small grains, absorb a single photon, a UV photon, de-excite and emit that. And so the amount of emission you get out is directly proportional to what you put in. So it's a linear relationship between the emission and the radiation field strength that is illuminating them. At the longer wavelengths, these grains come into equilibrium with the radiation field. They absorb many photons and heat up to an equilibrium temperature. And so you can see as you increase the radiation field, the peak of the dust emission marches to shorter wavelengths. This is the signature of the equilibrium behavior where the temperature of the grains is set by the radiation field intensity. So for mapping the PAH abundance, what we can do, in the best case scenario, is we measure how much dust there is from this peak, and we measure the strength of the radiation field. And then we can compare to what we see in the stochastic part and work out what the fraction of the dust mass in the form of PAHs is. So this is what we would call kind of a gold standard. We use far infrared observations to measure this part, and then mid-infrared observations to get the PAHs. So the not quite as great, but still really useful version of this involves infrared only, mid-infrared only, where here we compare the stochastic emission of the PAHs to stochastic emission from other grains as well. So at the longer wavelength side of this, at around 20 microns, there is small dust grains that are also stochastically heated, where we can use those as a comparison basis. And this gets us a mid-infrared only tracer of the PAH fraction, which we call R PAH. So why do we want to do this? Is because the jump in resolution with JWST is so huge that we would love to have a tracer that works at JWST resolution. So to give you an idea, this is the PSF, as the full width half max of the PSF. So the angular resolution as a function of wavelength for JWST at NIRCam and then at MIRI. And to compare, this is a factor of 7 or 8 times better than what you could do at the same wavelength, right? So what this translates to is the ability in a nearby galaxy, like M51 for instance, to resolve scales of something like 30 parsecs with the MIRI filters at their longest wavelength. And this, for comparison, is a beautiful map of the Orion molecular cloud created on the rooftop telescope that I don't know if is here still, but I spent some time refilling dewars when I was at undergrad. This tells us the amazing scales we can now see in nearby galaxies. So that was the goal of the PHANGs, so Physics at High Angular Resolution in Nearby Galaxies JWST survey. PHANGs, I bet you have heard about because Eric is a key player, and there's a lot of folks here who are interested in this, but just as a recap, this is a multi-wavelength survey of nearby galaxies led by Ava Schinnerer, Adam Leroy, Eric Roslowski, Janice Lee, and various other folks, Eric Emsalem. We have now covered around 90 galaxies with ALMA observations, and there is data as well from a variety of other sources, including VLT-MUSE, which gives you optical integral field spectroscopy, Hubble, giving very high resolution mapping of near UV to near IR. So PHANGs is a sample of around 90 main sequence star-forming galaxies that are close, such that 1 arcsecond is around 100 parsecs. They're not edge-on, and they're visible to ALMA. That sets the sample definition. Here you can see the galaxies that have now been covered with ALMA observations. And we observed many of these, now up to 75, I believe, with JWST as part of 2 treasury programs. So the first was led by Janice Lee. It covered 19 galaxies in a set of 8 filters, shown here. And this was followed up in cycle 2 with 55 additional galaxies in 6 filters. And the papers are listed here. If you want to get directed to the data, an easy way to remember this is phangs.org. It's also all en masse. All of this is a treasury, so is immediately public if you want to use it. And our current sample in the coverage of different instruments looks like this. So for 90 of the galaxies then we have CO. For a large subset, there is HST and JWST. And for a good chunk of the rest of that, there is actual optical IFU spectroscopy over the disk. So to show off a little bit, here's a beautiful press release image showing all 19 of the first cycle 1 galaxies, and a little zoom in showing half JWST, half HST. And you can see just the amazing resolution that we now have directly tracing dust in the ISM. So this is before you could see dust in the ISM, but indirectly kind of backlit by the stars. Now you can directly see the dust emission at comparable resolution. Great. So what have we learned about the PAH abundance? This is our first look. So here are the two components that are going to go into our tracer of PAH abundance. We have the PAH tracing filter, 770 wide, the long wavelength continuum filter that we're going to compare it to. And when you make the PAH fraction map, what you see looks like this. And hopefully this clearly comes through. There's all these little tiny dots where the PAH fraction is low. And those dots are H2 regions. We can do this a bit more quantitatively and show radial profiles of the PAH fraction as a function of the H alpha intensity over the total neutral gas surface density. And what you see is that as you get to H2 regions, this PAH abundance just tanks. So there's a very sharp cliff where when you are pointing at an H2 region, see a much lower PAH fraction. I'll come back to the second panel in just a moment, but there's more exciting things to do with this because we have so much information about the local environment. So what we can do is use the optical IFU data to select all of the H2 regions using the boundaries we measure in the MUSE maps. And then in those regions, pick out something that tells us about the conditions in the ionized gas. So for instance, this is the sulfur 3 over sulfur 2, which is the ionization parameter, which is telling you about the ionizing photons relative to the density in the region. And you can see a very strong correlation with the PAH fraction dropping as you get to higher and higher ionization parameter. This is a paper by Oleg Egorov, who's a postdoc in Heidelberg, and has another one coming out with all 70-some galaxies showing very similar result. So this is really exciting. This was just the first 4 galaxies. So what is this? Why is this correlated? This may be the result of, as we look at a 100 parsec region, we are mixing in some surrounding ISM with the actual H2 region that is completely devoid of PAHs. Or it could be that this is telling us something about what is actually destroying them. And these are kind of statistics that we've never had previously about what could be destroying PAHs. So a very interesting possibility. I just want to point out that we can also do this at similar resolution in very nearby galaxies in the far infrared. So this is now the kind of gold standard QPAH using far infrared observations. And in the LMC, you can see that every H2 region, which has this thick circle, is a dip in the PAH fraction, just like what we saw before. And so this is 10 parsec resolution map of this in the LMC. So this may be, we still have some regions in here at this resolution where we're capturing the surrounding neutral gas. So it's not perhaps completely clear of PAHs in these spots. So we can actually now zoom in even further in the Magellanic Clouds with JWST. And the resolution that you get with JWST in the Magellanic Clouds is kind of like a little mind-blowing. It's 0.00 something parsecs. So here is a region of the small Magellanic Cloud pointing right at the edge of a H2 region and the surrounding photodissociation region. So this yellow line shows you basically where that boundary is. And so I'm over here is showing the spectrum from this box right here. And you can see a perfectly lovely 3.3 micron PAH feature. So I'm going to step into the H2 region now in steps of something like 0.06 parsecs. And here is the next spectrum. The PAHs are very bright right on the edge because that's where the best UV photons are. So the very strong feature. But then the second you get in here, it drops to almost nothing within a few tenths of a parsec into the H2 region. So this is suggesting that whatever thing destroys the PAHs happens fast, right? This boundary is sharp. And also, when we look at nearby galaxies and we see every H2 region has a little dip in the PAH fraction, it means that this is happening quickly. So whatever the mechanism is that's destroying them is a rapid thing. And it also affects things all the way to the kiloparsec and galaxy scale. So this is a recent compilation of far infrared SED fitting for all of the 819 resolved galaxies that have Herschel data that are nearby. This is the summary of all the galaxies included. All of the data and fits are available if you'd like them on IPAC. And what I'm showing here is the PAH fraction as a function of the star formation rate surface density. And there's a strong negative correlation. So what this means is that when more of your ISM is filled up with H2 regions in a given kiloparsec, your PAH fraction drops. And this is very important, especially for people who are looking at galaxies that are starbursting and have huge star formation rate surface densities. The PAH fraction may be a lot lower than is expected. Okay, so moving back to this plot, what I want to show next is if we just chop out all of the H2 regions from a galaxy, you actually find a relatively constant PAH fraction among all of these galaxies. And this brings up an interesting possibility for using PAHs and their emission as a tracer of the total amount of gas. So just to back this up a little bit, what we expect for the infrared emission in the mid-infrared is this basic setup. So we have the gas surface density, we have the dust to gas ratio, and then the fraction of that that's PAHs. And because we are stochastically heating our dust, we have a linear proportionality with the radiation field intensity. So the mid-infrared intensity that we observe then should be just a very simple function of the PAH to gas ratio, the radiation field intensity, and the gas surface density. So if this stays about constant, and we understand what U is doing, we may have a great high-resolution map of the gas surface density. And this actually seems to work, which is cool. So here is a recent paper by Ryan Chown, who's a postdoc at Ohio State. What he did is took all 75 PHEREx galaxies, got just the region where we think they are molecular gas dominated in the centers, and compared the PAH emission at 770 with the CO in the place where molecular gas should make up most of the ISM gas mass. So here we see a quite nice linear correlation between the CO emission and the PAH emission, suggesting that we have a great tracer of the gas mass surface density. And here you can see a comparison of the map you would make from CO and the same map you would make from the PAH emission, just using this correlation. Okay, why do we care? We do have CO. We use that to figure this out. But the problem is, CO is also still quite hard to observe in galaxies. So it takes a long time to get to the sensitivity anywhere near what JWST does at the 770 wide filter in about 88 seconds, which was the exposure time for each of the PHEREx galaxies. So in the span of 88 seconds, the JWST images are equivalent to getting 2 solar masses per square parsec sensitivity at 3 sigma with something like 10 to 40 parsec resolution. And it is easy to go deeper. This was quite shallow. This far exceeds the sensitivity you can reach with ALMA in a reasonable amount of time, and it's impossible with current H1 observations, right? Because there's nothing that gets you close to this resolution, and also if you did get to that resolution, it is quite faint still to detect. So this is a really interesting possibility, and one of the possible applications here is using PAH emission at high resolution as your comparison to recent galaxy simulations that give us beautiful maps of the total gas surface density, but are more difficult to have the chemistry that gets you something like CO and H1 separately, right? Total gas is pretty easy. So this is an interesting image that was a tweet from Alex Pettit right after the first images of NGC 628 came from JWST. And half of this is a simulated galaxy, half of this is NGC 628, and you probably can tell which is which, but it takes you a minute, right? Like, it's actually a very visually compelling comparison. So if PAHs are well mixed with both the molecular and atomic gas, they may be one of our best high-resolution tracers of the ISM in nearby galaxies. So to take advantage of that, Eric and I did something that was kind of fun. So let me explain this real quick. So from the images of the galaxies you see in FANGs, you can tell that there are tons of holes in the ISM. So these are bubbles or shells driven by feedback. There's also voids because of dynamical effects in the disk. And you have bright sources as well. So Eric, who knows a ton about different topology statistics for galaxies and finding filaments and all kinds of interesting stuff, suggested using this statistic called the genus statistic, which tells you at a given surface brightness level in the galaxy whether it looks like holes or like sources. And in the terminology people use, this is being more Swiss cheese-like versus being like meatballs. So meatballs are sources, Swiss cheese is holes. The actual mechanism of this statistic is at a given intensity, you see how many connected structures there are below that intensity versus above, and the difference gives you this genus statistic. So if it's negative, it's like Swiss cheese. If it's positive, it's like meatballs. So we took the first 4 galaxies from FANGs and stepped through surface brightness in the galaxies and measured this statistic. And one thing that's cool is that you can see for at least 3 of these, the crossover between Swiss cheese-like, so holes, to meatballs, is around 10 solar masses per square parsec, which also turns out to be the approximate column density where you expect the ISM to become molecular. So below that, you expect it to be diffuse, atomic, maybe, and be pervaded by holes driven by feedback. And then above that becomes molecular, maybe self-gravitating structures that are more like sources than they are like diffuse filling medium. So we also were able to test this out on a couple of simulated galaxies and see similar behavior. So one of the things we're hoping to do soon is a whole slew of galaxies looking at this statistic and learn if we can find anything out about the column density where the ISM stops being Swiss cheese-like. One other cool application of using PAH emission as a gas tracer that I want to highlight is the ability to look at PDFs of the emission at high resolution. So this is work by Deb Patak, who's a grad student at Ohio State. And what Deb did is to take all of the galaxies, toss out the H2 regions where we know things are a little bit weird for the PAHs, and also get very bright, and look just at the diffuse ISM, and look at the PDF of the column density you would infer from the mid-infrared emission. And what Deb found is that this PDF is very constant over many different galaxies. And you can see the red version here. This is at all the different wavelengths. And the width of this PDF is actually consistent with what you would predict if this were isothermal turbulence with Mach numbers of between 5 and 15. So this is a pretty unique attempt to measure this PDF from the mid-infrared emission using the fact that it may be a good tracer of column density. Okay, so at this point, I've told you a lot about high metallicity galaxies where I've argued that the PAH abundance changes mostly in H2 regions and is pretty constant outside of them. So you may be wondering, does it change anywhere? Are PAHs always the same across the diffuse ISM of these galaxies? And the answer is really no. The way that they change, though, is primarily with metallicity. So as you go to lower and lower metallicity, these features disappear. So this is a Spitzer compilation where there's stacks of galaxy spectra as a function of metallicity. You can see that as you get down to 12 plus log over H of 8 or so, the PAH features become extremely weak and then are entirely gone. So there is something going on that makes PAHs it's very unhospitable for them in these low metallicity galaxies. Beyond that, we can actually see a pretty dramatic shift in the PAH fraction, even in the local group, just between the LMC and the SMC. So in the LMC, outside of H2 regions, PAH fraction is basically the same as the Milky Way. It's really unaffected by the slightly lower metallicity. But then you go to the SMC, and we have to even rescale this axis to show you anything because the PAHs are very rare in the SMC. So at around the SMC's metallicity, something happens where they are just gone. And this dramatic deficit of PAHs as a function of metallicity is important for a number of reasons, including that people are now trying to observe these things in galaxies at higher redshift that may have very different metallicities than things we're used to in the local universe. So this is an interesting problem. There are a couple of potential explanations. One of those is impeded formation. So in low metallicity conditions, you just have less carbon. If your rate of forming these grains requires 2 carbons to meet and to continue to meet other carbons, then you will form them less efficiently, and you would probably prefer making smaller ones because making bigger ones just requires continuing to meet more and more carbon atoms. So this is one route that could potentially explain this low abundance. Another that's been quite popular is the enhanced destruction mode. So here in low metallicity galaxies, your UV field is both harder and more pervasive because the shielding from other dust grains is lower. And so you are just better at destroying the PAHs throughout your ISM. If this is the case, you might expect actually that the most fragile PAHs should be particularly gone, and that is small ones. So small PAHs are easier to destroy with a single photon or with any process really would destroy the smallest ones first. So these are 2 different predictions. You might, in this case, predict PAHs are smaller on average. And in this case, you might predict they're bigger because the small ones get destroyed first. So there's new information that lets us look at this. So this is work by Corey Whitcomb, who's a PhD student in Toledo. He looked at 3 galaxies with large metallicity gradients across their disks and mapped the PAH fraction, which you can see here. And there's basically a sharp drop at low metallicity. And then he also looked at the individual features and how they each change as you go past this metallicity. So what he found, and this is summarized here, is that as you go down in metallicity, the PAH features that are coming from large grains, so that's 17, that's 12, that is 11.3, they decrease relative to the others. But the features coming from small grains, like our friend 6.2 here, 7.7, and then this is a prediction for 3.3, they increase. So what this is saying, as we get to the lowest metallicities, the PAHs are the smallest, which tends to favor this idea of impeded formation rather than enhanced destruction. So I think this will be a really interesting thing to test spectroscopically with JWST and go to larger samples of galaxies in more low metallicity environments to see if this trend holds up. So speaking of spectroscopy, in the last couple of minutes, I want to spend a bit of time talking about some of the new things we've learned with JWST spectroscopy. This is a summary of some of the interesting weaker features and some of the stronger ones that we can look at to learn things about the PAHs. This is a Spitzer spectrum, and there's a feature I want to zoom in on that you can't even see here, but turns out to be very cool, which I'm going to focus on for the last few minutes. So it's down here at about 4.6 microns. There is a feature that comes from deuterated aliphatic hydrocarbons. So this is work that was on the archive just at the beginning of the week and is a product of the M51 Treasury Survey, which I've been leading with Danny Dale at Wyoming. We covered a good chunk of M51, which you can see here, with all of the interesting photometric filters for the ISM, and then 3 strips of spectroscopy with both the near spec and MIRI IFUs on JWST. And for this purpose, for this paper, have extracted the spectrum of these 3 really bright H2 regions that are at the center of the strips. So actually 4 H2 regions that are at the centers of these strips. So here is what the 4.6 micron spectra look like. And this is pretty, I don't know, there's so much going on here that I never even knew about before JWST. Really beautiful spectra. So in addition to the PAH features that are off of this plot, there are some interesting ices, CO2 ice. There's this XCN or OCN, O-CN ice I am not super familiar with, but that these are things that actually SPHEREx is going to be amazing for shortly in the Milky Way and elsewhere. But then here you can see underlying some of these bright emission lines this little hump. This turns out to be the vibrational mode of when you replace a hydrogen with a deuterium atom and just shift that 3.3 and 3.4 feature slightly to longer wavelengths. So we have detected this in 50 parsec scales in M51, which is pretty amazing. If you calculate comparing the non-deuterated and the deuterated version, you can work out what a D to H ratio for the aliphatic hydrocarbons is, and it's huge. It's 0.17, which is 10,000 times above the ISM, so the typical ISM value. And in fact, in M51, the deuteration is 2 to 3 times higher than in the Orion bar, which is a comparison spectrum, and similar to what's in M17. So these are some early Milky Way observations that show us the same feature. The other interesting thing about this is there's no detection of the aromatic version of the CD stretch. So this suggests that there's preferentially something about the aliphatic material that likes to be deuterated. So an interesting thing about deuteration or the D to H ratio in the ISM is that you have a really strong expectation for what it should be just based on the amount of deuterium predicted made in the Big Bang. So there's a tiny bit you could remove by putting that gas and making it cycle through stars, right? This is astration, gets rid of some of your deuterium. But when you go out and observe through the Milky Way's ISM, there's a huge range of observed D to H that's far lower than this. So you can see a ton of scatter, over in the very low column densities, maybe it's around 15 parts per million. Then there's a ton of scatter, maybe it's lower here at high column densities. But it's again been kind of a long-standing question, where is this deuterium? Because it's not reasonable to expect that change with astration alone. And people have argued that this must be the case where you incorporate your deuterium into hydrocarbons. So this detection of this strong deuterated aliphatic hydrocarbon actually bears that out. And the deuteration that you observe is sufficient to explain this kind of scatter, if this is typically how much of your deuterium you put into the hydrocarbons. So this is pretty cool. One of the things it suggests is that there has to be a lot of rapid changes in D to H in the dust in order to make this aliphatic material have such a variable deuteration. But this is actually the start of kind of a new whole sequence of spectroscopy for PAHs, spectroscopy of deuterated PAHs. This is the new frontier that JWST enables. So with that, I just want to point out this is the beginning of what we're going to learn with JWST spectroscopy of PAHs. There's a ton of other little features that we haven't explored yet. It's actually hard to even categorize some of the large number of things that you see. And because of the amazing data that is soon to be coming from SPHEREx, which was launched in March 2025, in theory, we are soon about to be able to make a spectral map of the 3.3, 3.4, maybe even 4.6 features for tons of the ISM in the Milky Way, almost every nearby galaxy, can stack everything together. The possibilities here are quite endless, so I'm very excited to see the first data from SPHEREx coming soon. So with that, let me just briefly summarize. So I hope I've convinced you to be excited about PAHs. We know a few things, but there are so many more things to learn. We know that they are destroyed rapidly in H2 regions by a process that is not perhaps completely well understood. Outside of H2 regions, in metal-rich galaxies like the Milky Way, the abundance is fairly constant, and this actually lets us use PAH emission as a gas tracer, which opens up a whole range of possibilities and gets us past some limitations of what you can do with actually just directly mapping gas with ALMA and various H1 telescopes. So they also, I didn't cover this, have a quite unexpectedly constant size and charge, but they disappear quite dramatically, very steeply at around 8.1 in metallicity for reasons that most likely have to do with impeded formation of PAHs, but people will fight me about that, so I'm happy to debate. Other people really like the destruction mechanism. And then they also apparently have variable aliphatic content and deuteration at levels that explain missing deuterium from the ISM. So we are just on the verge of much more information about this from JWST and SPHEREx, so thanks for letting me talk about it here. Happy to take any questions.
Thanks, Karin, for the wonderful talk. Do we have any questions for Karin?
This is so. Oh, it is on. Can you hear me?
I can hear you. I can repeat it if it's...
Okay. So this was so cool. Thank you. So you talked a lot about how these PAHs are destroyed in H2 regions, but then at the beginning you said that they could be both formed and destroyed in supernova remnants or supernova shells potentially. Can you talk a little bit more about that and whether it's mostly destruction or maybe a little bit of formation or how that works?
Right. So if the formation would be shattering of other grains.
Okay.
I'm not 100% convinced that that would happen in a way that would net you PAHs.
Yeah.
I think you might just actually destroy all of the dust.
Okay.
And I think probably that's not the best mechanism for forming them because of that. In theory, if you have shattering in other situations that are not quite as dramatic, like lower velocity shocks, for instance, maybe you can be continually creating these small fragments that then get turned into PAHs if they rid themselves of all the fragile stuff. That one, I feel like I'm probably, personally, I think it's more likely that it's some ISM formation route that's either some combination of gas phase or ices on the surfaces of grains that let a chemical reaction happen that forms PAHs. But I don't think we have any direct evidence for that just yet. But yeah.
Earlier you had a slide with the H2 region and like the cells that you were taking spectra for each cell. And I noticed that in that slide, even in the cells that are deep in the H2 region, you can still see some features, in particular the 3.3 feature. And I guess I'm curious related to...
You mean this
yeah,
little...
exactly, the red line.
Yeah.
I see that you can even, again, I'm wondering if you can get any like evidence or information in terms of like the ratio of the small PAHs to the big PAHs, and whether that, are they uniformly destroyed, or can you actually get some evidence here for even what may happen in the low metallicity galaxies, if they're getting destroyed or not, depending on what happens here, because if you are confident that what's happening here is destruction, then maybe you can see the same effect here. I'm wondering
I think that's a great idea. So that hasn't, I haven't made that measurement yet, but that is a really good approach to this, I think. And I agree that if you squint, you can still see something here. This is most likely that none of these lines of sight are ever cleanly like one thing or the other. We're always looking through, the ISM on the front and the back of this thing. In this particular case, more than most, I think it's cleaner. Like in the Milky Way, it's really hard to not be confused with the rest of the ISM along the line of sight to any given H2 region, right? So it's actually trickier than it sounds to make the measurement of like, is this gas truly free of PAHs within the H2 region? But I agree, your suggestion is a really good one to try to see how these things vary comparatively between the bigger PAHs and the smaller PAHs. Mm-hmm.
Thanks, Karin, for sharing your love with PAHs with us. I'm wondering about correlation with LVN, in particular in this region, right?
Yeah.
In 13. There is already, or will be very soon, all these diagnostic emission lines that give you stuff about the hardness, the spatial variations of the interstellar, or the radiation field in these H2 regions. Have you thought about correlating the JWST data with these data?
So, especially for the Magellanic Clouds, yes. I technically am not part of LVM, but I know that a lot of people are, and I think that would be a really interesting thing to do. And in fact, the dust map, I don't know if I have this in it. Oh yes, this dust map is public. If anyone wants to look at how the this correlates with the properties of the H2 regions, I think that would be very interesting to try. And LVM will be great for this. I've seen some of the data in presentations, and it looks outstanding. So, yeah.
Do we have any more questions for Karin? And I'm assuming there's no online. All right. Well, if not, let's thank Karin for the fantastic talk.